Hello, my amazing students. This is Mrs. A, and I'm going to attempt to do 5.3 here before I crash and burn. I've had company all weekend, so I'm a little bit tired, but y'all have a test this week, so I'm going to try to finish up as much as I can. So we are on 5.3, and we are graphing the natural log function here for the first question. And again, I'm going through the questions that are on our little PowerPoint at the end, just because this is my test bank and I want to give you as many examples of what you could have on a test. So when we're graphing the natural log, we're going to basically think about remember the natural log is the inverse of the e function, or the exponential function base e. So the logarithm is always going to go through 1, 0 as its little anchor point unless it is translated somewhere else. And the logarithmic function should go kind of like this. It approaches the y axis as its asymptote. So this should be what the logarithmic function generally looks like. But of course, we need to put in some values if we're going to see more exactly what it looks like. So if I were going to say, since this is log base e, that's what the natural log is, then at e, log base e of e would be 1. And since e is about 2.7, I'm going to think if this is 1, and then I'm supposed to go to 0.7-ish, and then my value is supposed to be 1. Okay, so I could say e, comma, 1 would be a point. Okay, so it would be about there, and that looks good to me. All right, so the next one we're going to do is 6 to the 4th power. And this is a base 6. Hold on, I think that might be 6 to the y power. Yes, it was supposed to be a variable. So this is 6 to the y power. And anytime we have our variable inside our exponent, then it is an exponential equation. Now, this one is going to be switched somewhat because the x and the y are switched. So basically, a y is 6 to the x function would be curving up like an exponential. But notice they have switched the x and the y. So this is actually a logarithm function, because remember, to find the inverse, we switch the x and the y. So here I'm taking an exponential equation, which goes through 0, 1 and goes up this way, and I have switched the x and the y, so this function instead should go through here. Okay, so if I were going to look for an exact point that's supposed to be on this graph to plug it in, I know that 6, so we're doing this one right here. If y is 0, x is 1. So if y is 0, that's my x-intercept, x is 1. If y was 1, x would be 6. So we go all the way over here to 6, and we can make 6 maybe right there. Okay, at 6, I would go up to 1, so it would be a little tighter to the x-axis than my e curve that I just graphed, my natural log of e. Okay, so we could say that the point would be 6, 1 would be a point on this graph. If I let y be 2, that would not happen until x was 36. So you can see all the way out to 36 before I raise up 2 steps. So that would be an accurate graph of that function. Okay, so the next one that we're going to do are 3 and 4 together on the same page. And we're basically talking about what is the definition of a logarithm. And a logarithm is an exponent to which you raise the base 10 to get 10,000. Well, there's 4 zeros out there, so I'm going to have to raise 10 to the 4th power. Therefore, the log base 10 of 10,000 is 4. And that's all I have to do with that one. Okay, so then the next one is log base 22 of 22. And since the logarithm is the exponent, to which I have to raise 22 to get 22, since 22 is already 22, that answer is 1. So the log 22 of 22 is 1. In fact, log, we could say log base n of n is always going to be 1. Okay, so then we're doing the next two problems. And here we're to take these two exponential equations and turn them into logarithmic equations. So basically, again, the definition, the log is the exponent. Well, in this first one, -3 is the exponent. So we could say log base e is -3, and then the argument is going to go right here. Okay, so 0.04979. And the only thing I would do to improve that is to say that log base e is natural log. So I'm going to take that off and turn log base e into natural log. And then I have a good answer. So natural log of 0.04979 is -3. That's accurate. Okay, so to me it's a little bit easier to go the other way. That's a log base e. E to the -3 is the argument. Okay, so now we got 2 cubed is 8, which is true, but we're to turn it around into its logarithmic form. So we're going to say the log is the exponent. Well, 3 is the exponent. Okay, so we'll put log base 2, because that's the base. Log base 2 of 8 is 3. 2 cubed is 8. So those would be both of those turned around into their logarithmic forms accurately. Okay, so now we're doing the vice versa of this one. We're going to turn each one of these logarithmic statements into the equivalent exponential equation. So to me, this is a little bit easier. You just take the base, raise it to what's over there, and you get the argument. So we get 2 to the 7 is t to the 9. Okay, so that is equivalent to what we have there. All right, and then over here, since this is log base e, we're going to have e to the 3.3673 equals, okay, so e to the that is 29. And those are the two answers for that one. Okay, those are correct. All right, so now we are working on number 9 and number 10, and we are to evaluate this using our calculator. Now let's think a minute. This first one should be doable, because remember what the logarithm looks like. Okay, the log comes down here and it approaches an asymptote. It goes through 1, 0, and it goes off in that direction. That's your typical logarithm. The logarithm is defined in between 0 and it cannot be, we can have a log of 1 is 0. We cannot have a log of 0 because it's approaching an asymptote. And this logarithm here, because it's between 0 and 1, should be negative, because the log is always 0 unless it's translated somewhere else in between 0 and 1. It does not exist at 0, and there's nothing over here. So this one should be a no-go. It does not exist. So we'll just put does not exist. And if you put it into your calculator, it's going to give you an error. Okay, it does not exist. Let me get my calculator here, and we'll put this other one in the calculator for you, which I dropped on the floor. Okay, so we're going to do log of 0.0803, and we should get a negative number. And I didn't hit enter. Now we got a negative number. Negative 1.0953, and that would be what it is rounded. Okay, so we need to remember how the logarithm acts. So now we are doing a change of base form here. And when we're doing a change of base form, we're going to always, I usually go to base 10. We could do it with base 10 or base E. But let's just take log over log, and we're going to use just base 10. So I'm going to leave just log base 10. The base of the original problem goes down to the basement of the new problem, and the argument goes upstairs. So in our calculator, we're just going to do the log of 70.07 divided by the log of 5. So I'm going to put those on my calculator here. So I'm going to do log of 70.07, and I'm going to divide it by the log of 5. Okay, and I end up getting 2.6404 on the answer key here. 2.6404 looks good on there as well. Can you see that? All right, so now we're going to do the next one, and the next one involves a decimal for our base, but that's okay. Remember the rules for the base. You cannot have a negative base. It doesn't work. And you can't have a zero base. But if your base is a decimal, that's not a problem. So we're going to go ahead and use our change of base. So we're going to do log and log. Okay. And we're going to put the base of the original problem downstairs in the basement. And the argument is going to go upstairs, and so we're going to put log of 205 over log of 4.8, and I could do natural log of 205 over natural log of 4.8, either one, as long as I'm using the same logarithm both directions. So I'm going to plug in, I tell you what, I'm going to put natural log in instead of log, just to show you that we can get the same answer. So natural log of 205, and then divide it by a natural log of 4.8, and I used natural logs instead of regular logs that time, and I ended up with 3.3934 from my answer key, and that looks good right there. Okay, so that is finding a log using the change of base formula. So now what we're going to do, number 13, is we're going to graph the function and its inverse on the same set of axes. Okay, so we know that the log function and the 10 to the x, because log is log base 10, so these are inverses of each other. So when I graph them, we're going to pick 2 points for each one because we know what the general log looks like. So basically, since this is log base 10, then don't I know that log base 10 of 10 is 1. So 10, 1 would be one of my points for my first one. And 102. 102. Okay, the log is the exponent to which I raise the base 10 to get the argument 100. Okay, so I'm going to go way out there. So now we think about our anchor point that we usually have here, which is 1, 0. And does that work as well? So basically, if we think of, we have log base 10. So 10 to the 0 power is 1. And that works, right? So we're going to say 1, 0 would be one of our points. So we can go ahead and graph that one. So we have 1, 0, and way out here, maybe 10 right there, and a 1 right there. So it's going to be pretty tight to that axis. Okay, so now what about this one right here, 10 to the x? Won't that be pretty tight to the y-axis there? So it's going to go through the point. Remember, each one of these points are going to flip because it's an inverse. So instead of 10, 1, we're going to have 1, 10. So when we get to 1, we're going to go way up there to 10, and we're going to go up there and down there. And it's not going to touch the axes. Okay, so that one was number 13. And notice that the two inverses will reflect across that y is equal to x line there, always. Okay, so now let's look at the next one, number 14. And we have negative 3 log of x. And then we have 10 to the x divided by negative 3. So this is number 14 here. And let's look at what's going on here. So basically, isn't this logarithm here, it's got a negative 3, so it's going to be reflected across the x-axis. Okay, so basically, this one is going to be negative 3 is going to reflect it down. So we had this one. If we were thinking about just the log, it would be going this way, right? That's our normal logarithm. But now, since it's got a negative in the front, isn't it going to flip this way? And this little point here should be going up here, and this thing should be going down like this. So it should be looking something like that. So let's plug in a few points to get a little bit of accuracy in here. So, because that's a stretch also. So it's probably going to be maybe coming down here a little bit further. But let's throw a few points in. So let's say we're working on this first one. If I plug in a 0, I can't take a log of 0. It doesn't exist, so let's don't do that. Let's throw in a 1. Okay, if we throw in a 1, then log base 10 of 1 is going to be 0. Okay, and I multiply that by 0, and I still have 0. Okay, so 1, 0 still works. Okay, if I throw in a 10, which since this is log base 10 would be a good point to use. So log base 10 of 10 is 1, but then I multiply that 1 by a negative 3, and I'm going to get a negative 3. So when I come out here to 10, I'm going to go down to negative 3. So it's probably not quite that. So let's say way out here to 10, negative 3. We'll say, okay, it's going definitely not as sharp as the other one was. Okay, and then of course I'd go out to 100, and I would normally be at 2, but since I'm multiplying by negative 3, I'd be at negative 6. Okay, so that's a pretty good graph for that one. So now let's look at the other one, and we're talking about the inverse of this one. Okay, so we're going to just flip the points, and since we had 1, 0, it's going to be 0, 1. Okay, and then since we had 10, negative 3, it's going to be negative 3, 10. Okay, so negative 3, 10 is going to go way up there. And so let's throw in a point over here. We had this thing going up to the axis. So if we plugged in a 1/10, a 1/10 would get very close to this axis, wouldn't it? We'd be moving this way on this one. If I threw in a 1/10, then wouldn't I get a -1? Okay, and then the -1 times the -3 would be a +3, and I would be up here. So let's plug in 1/10 and a +3. So then that gives me another point when I get my inverse. And at 3, I would be at 1/10. So at 3, 1, 2, 3, I would be at 1/10. So this one is coming this way and approaching this axis as an asymptote. And that's what it's supposed to look like. All right, so now we're working on number 15, and we are to discuss the change, what transformation is happening to get from natural log of x to 3 times natural log of x, and this should just be a vertical stretch. So vertical stretch is all we needed to put there, vertical stretch of 3 if we wanted to, but that is a vertical stretch. Okay, so we're doing the same thing on this one, which is talking about number 16 here. And we're going to assume that the base function is just log base 4 of x. So we're saying, what is happening here? Well, we have a negative in front of the log, so this is going to be a reflection across the x-axis because it's happening outside of the function. So we're going to reflect across the x-axis. And what is the 4 going to do? It's a +4, so it's going to move us 4 steps up, and that should be our transformation there. Reflected across the x-axis, moved 4 steps up is correct. Okay, on this one, we are number 17, we are to find the domain and the vertical asymptote. And when we look inside here, the domain, remember your argument can never be negative or 0. You cannot have a log of 0. And again, this is because our logarithmic graph is always going to come up here to the right of 0. There's nothing over here. So we can basically say that x plus 4 must be greater than or equal to 0. So if x plus 4 is greater than, not equal to 0, excuse me, only greater than 0, then we'd have x must be greater than -4. Okay, so this one is going to have an asymptote. The vertical asymptote now is going to be sliding over here to -4. Well, that's a really crooked line. And then our graph is going to slide accordingly to this side over here. So this is going to be vertical asymptote now of -4, and that should be our graph. So our domain is going to go from -4 to infinity. So domain is -4, but not touching -4 to infinity. Okay, the next one, we're doing the same thing. Now this 5 is outside the function, so it has nothing to do with the domain. It's going to move it up 5 steps. So this is going to be our basic logarithmic function, log base 3 of x, no change. So this is going to have a vertical asymptote of the y-axis, which is x is equal to 0. That's our vertical asymptote. And the domain will be from 0, but not including 0, to positive infinity. And that should be and is accurate. Okay, so now we're going to do a piecewise function here with only 2 parts in it. So we're going to say less than or equal to 2 or greater than 2. So here's our graph, and we have a 2, and I'm just going to put our little zone there so we know, okay, one thing happens up to here, and then we go into a new kingdom and with a new ruler. So in the first kingdom, the ruler is a line, x plus 2. So he's the rule for the region over here. And so I'm going to think, since I'm going to put a darkened circle at 2, I'm going to say, okay, when I plug in a 2, then a 2 plus a 2 is a 4. So at 2, 1, 2, 3, 4, I should have a darkened circle. And this thing is going through, since this is a slope and y-intercept, it's a slope of 1 and a y-intercept of 2. So we're going to go through that point right there as well. And if we went in a negative 2, we would go out of 0. So we can go all the way up to there. We know it's a line. There we go. And then to the right of 2, a new function takes rule, and it's the natural log of x minus 2, which is going to be the natural log function slid 2 steps to the right. Okay, so let's think about that special point. That special point is usually 1, 0. That's our anchor point for the log. But now if this is being moved 2 steps to the right, then we're going to be anchoring at 3, 0. So let's plug in 3, 0. If we plug in a 3, then 3 take away 2 is 1, and log base anything of 1 is 0. Okay, so when we plug in a 3, we get out a 0. So there's our anchor point, but he's been moved 2 places to the right. And since the rest of it is just a log function, shouldn't it approach this one and then go off in that direction? Pretty much like that. And that's what it should look like. Okay, so now we're on number 21, which was a word problem, and I had to look at it a little bit before I knew exactly what we were doing because of the wording. It says, if an earthquake measured 8.3 on the Richter scale, what was the intensity of the earthquake in terms of I.O.? The magnitude on the Richter scale of an earthquake of intensity I is log base 10 of I divided by I.O. So, this is your equation. So basically, you put the 8.3 that they gave you over here, and then we're trying to write the intensity in terms of the I.O. So we take this formula that they gave us, we set it equal to the 8.3. Now what happens when we turn this logarithm around, we get 10 to the 8.3 as the argument, which is I over I.O. So this is our new equation. So we've got 10 to the 8.3 is I over I.O., just turning the logarithm into an exponential. And then we have 10 to the 8th 0.3 times the I.O. that's in the denominator. In other words, we're cross multiplying actually. And so we've got this, or multiplying both sides by I.O. And we end up with this is equal to the intensity. And when we put this in the calculator, we get this long answer times the I.O. And that is the answer. And that's the correct answer. So that is a earthquake problem. All right, so this is the last one that is going to be on 5.3, so we're almost done. Okay, so it says the loudness, D, in decibels of a sound of intensity I is given by this formula right here. D is equal to 10 log of I divided by I.O., where I is measured in watts per meter squared, and I.O. is equal to 10 to the negative 12 watts per meter squared. What is the decibel level, D, of a noise whose intensity is 7.54 times 10 to the negative 5? Okay, so all we have to do is take 7.54 times 10 to the negative 5, and we have to divide it by 1 times 10 to the negative 2, which is what they gave us as a constant for I sub O. And once we do that, we get this. And then, according to the formula, we just take 10 times the log of this, and we should get our answer. So when I plug that in, I had up here at the top, I put the logarithm in, and then after I got the logarithm answer, I multiplied it by 10, and I got 78.77, and they rounded it in your book to 79. But that is how you do an intensity of sound problem or decibel problem. And we are done with 5.3, and we'll be moving on to 5.4, but not tonight. I'm pretty tired. So this is Mrs. A, and may God bless your day.